And let's start doing the share screen. And so again, if something bad happens to the connection, then don't get despair. Do that. Simply wait and I will reconnect you. Okay, so we're going slower than I was hoping to. I'll try to speed up a little bit because the general plan for today is to complete the discussion about sort of the introduction to the standard model that we're having, and then having a tutorial, which will be about the standard model. After the tutorial, I will post the next problem set. I saw that several of you did it, so that's great. I'll have a look at them as soon as I can. And if we have time, then we won't be delayed, and we go straight to the next subject, which is decays and scatterings. This is the general plan for today. So very briefly, we recap, right? We're still dealing with the standard model. Quick recap. The basics of the standard model. We spoke about the fundamental fermions. We spoke about the interaction. We spoke about quarks and forces, about Feynman diagrams, and the fundamental how the Feynman diagrams represent processes. We mentioned Mandelstam variables, buzzwords to remind you where we are. I will post some of my lecture notes online at a certain point, but I need to adjust them, so it's just taking time. Mandelstam variables. Then we spoke about mesons, right? We spoke about decay, sorry, we spoke about decay via weak interactions. Okay, some noise, I don't know where it is coming from. We spoke about mesons. I gave you I mentioned the idea of an isospin, which is analog to spin. And that relates to the symmetry groups of the mesons. That's why the pi 0, so that the pion plus is composed of up and anti-down quark, the pion minus is anti-up and the down quark, and the pion 0 is a combination, one over square root of 2 of up, up, bar minus down, down bar. And then I spoke about excited hadrons. Right, excited, we have hadrons, which you can think of the hadrons as a ground state of the quarks, but then there are higher states, which are not ground states. So higher spin, higher orbital angular momentum, not to be confused with the isospin, right? Higher radial excitation, and that give us to new particles such as the rho and the delta. And of course, there are particles which are made out of different quarks, like the kaon, which is made of the up and the strange, anti-strange, etc. So there is a plethora of possibilities how to take these that have and made a large number of particles. Now you can read all about it in what's called particle data group. It's called the PDG. Actually, I'm going to give you in the homework. I'm going to send you there to read a little bit and see a little bit about that. Now quarks, we say that they are different than the leptons because they carry the strong force. And this is the reason why we do not see them as independent particles. And that is also why it took many years for people to believe in them. Because the hypothesis of a color confinement The color is the carrier of the strong force. Right? And the color confinement means that colored objects are always confined such that what we can see is a color neutral. So there are three colors which are classically denoted by blue, green, and red, but we cannot see them. We can only see color neutral objects. So color neutral meaning that they are made of either all three, one blue, one green, and one red, which makes them neutral, or a blue and an anti-blue, quark and an anti-quark. And these are known as mesons. So the color neutral, we only see color neutral objects. So due to the color confinement, the single quark live in size of a typical one Fermi. That's the size of a proton, right? What happens if we try to take away quarks from each other? So let's say we have a pair of a quark and anti-quark, and they are confined by the gluons. So when we try to push them apart, what will happen is, because the gluons themselves carry a color, then there will be other gluons that will connect the gluons with themselves. This is something which can happen. And so it will just stretch it. And that's going to end up with an increase in the energy density. So the energy density in the field is going to be proportional to the distance. Sorry, the energy density is fixed, but so the total energy is going to be proportional to the distance. The total energy, V of R, is going to be linear with the distance, where K is 1 GeV per Fermi. So in SI units, this is 1.6 and 10 to the minus 10 divided by 10 to the minus 15. That's of the order of 10 to the 5 Newton, which is a huge number when it acts on a small quark. This is as opposed to what happens if we have particles that only interact via, say, the electromagnetic charge, electron and positron, right? If you try to take them away from each other, then the field lines will simply stretch and they'll become weaker. And then the last thing we spoke about was jets. So, okay, so what happens if we try to take away a quark from its friends, right? Of course, we cannot just push it away. We can kick it, let's say with an electron. So we have an electron that kicks in. Excuse me for that. We have an electron that interacts with the proton, right? And so it interacts with one of the quarks in the proton. So a proton is made of 2 up quarks and 1 down quark. And they are glued together, right, by these gluons, right? So the up quark will be kicked off, but when it gets to distances of more than roughly a Fermi, then the energy of the gluon tube will become large enough to produce a new pair of quark-antiquark, right? So something like that. We'll have a down and anti-down. Right. So we might end up at the end of the day producing a neutron and a charged pion. Of course, if we increase the energy of the kick, then we simply produce more particles. So the outcome is what you're seeing in these experiments that you're seeing in CERN, this jet of particles, many of them are mesons. Mostly it would be mesons, because if you kick out again, then you get more mesons. And they will all be moving in the same direction as the initial quark. Right. So yeah, so the end result is that you end up with a jet made of semi-stable particles from the energetic quarks. Now, some of them, if they're not stable, they will simply decay to other particles, and that's what you're going to see. Right, I think this is as far as we managed to went through last time before the reality bite us and we had to shut down because of connectivity problems. So before I proceed, I want to finish 1.5 more topics and then do the tutorial and then go to the next subject. But before we do that, then I want to stop and ask you if you have any questions.
You use the letter K in the potential. Is that, but it's force. It's not a spring constant.
No, there's no string here. Right? It's potential.
So K is just a force.
K has units of, yeah, it's a force, right? Energy per distance, yeah. Any further questions? Okay, so there was another point that I mentioned I want to say a few words about, and this is the issue about the running coupling constant. This is something which you might have heard of. So let's do it in a somewhat ordered way. So I told you that one of the problems of doing calculations in QCD, the quantum chromodynamics, right, the strong force, is that the coupling constant is of the order of unity. So it's not a perturbative theory. So we cannot really do perturbation calculation in QCD the same way as we're doing in quantum electrodynamics or with the weak interactions. However, fortunately, right, for the ability to do calculations, when we go to high energies, the coupling constant of QCD decreases. Sorry, there was a question?
No,
this is not related to the lecture, then it's not related. Okay. So heuristically, what happens is that the coupling constant of QCD, actually not of QCD, all the coupling constants, they depend on the length, or which is inversely proportional to the energy, right? Depend on the length, inversely proportional to the energy. So that's the name running coupling constants. So I have a figure that I actually copied from the book by Thompson, so you can find it there, which looks how alpha S, the coupling constant of QCD, changes with the energy in the center of mass. So these are experimental results. I'm just going to sketch it, right? So this is the energy in GeV. It's a 1, 10, 100. And the coupling constant, we said it's about unity, but it goes something like that. Let's say this is 0.1 or so, at around 100 GeV. roughly. And there are experimental data from various experiments, the tau decay, the electron positron annihilation, etc. So what really happens here? So what really happens, just to give you again heuristic arguments, is that the coupling constant is a simplification of a more complex physics. So how can we understand that? So the thing to realize is that the vacuum, in fact, when we speak in the realm of particle physics, is really a dielectric material. Let me write it down because this seems counterintuitive. Definitely it's not a classical result. Vacuum is a dielectric material. Right. Just to remind you that the dielectric material is a material, it's an insulator which can be polarized when an electric field is applied. Right. This is an insulator that can be polarized when an electric field is applied. Okay, so what does it mean? Let's say that I have a dielectric material, right? And I put a charge Q inside the dielectric material, right? So this is a dielectric material. Dielectric material. And I put a charge Q in it, right? What happens? The molecules of this material, they start orienting themselves, right? Such that the electric field is being screened, right? So I have a material, it's made of molecules. Let's say this is a minus charge. Then you have a plus, minus, right? Plus, minus, something like, you know, you're familiar with this picture from classical E&M, right? So what happens is that the effective field seen by a distant observer, right? So if the observer sits somewhere over here, right? The effective field is, we call it Q over epsilon, right? Where epsilon we call the dielectric constant. This is effective field, right? So, you know, the use of this concept of a dielectric constant enable us to use the, you know, the same theory, Coulomb's law, without the need to write the details of the complex interactions between the charge and the molecules, right? Now, another point to note is that, you know, if we're getting close, if the observer gets closer and closer to the charge, right? When it gets closer than the size of a molecule, right? Then it feels again the full charge, right? Because there are no molecules that screen it, right? So effectively, we can think of a dielectric material as producing an effective dependence of the charge on the distance, right? So we have Q becomes in the dielectric material, Q of R, right? You all familiar with dielectric materials from your electromagnetism course, right? I hope so. Yes, okay, good. Now what happens in vacuum? So we have no material. Well, the thing is that we have in QED, right, we have perturbations, right? So if we have a charge, right, the electric field in a charge, we say, is mediated to lowest order, right, by a single photon, right? So how do we have, how the other particles know that there is another charge in there, right? They exchange these virtual photons, right? But this is to lowest order, right? But but this photon then can produce another pair of virtual electron-positron pairs, right? So you have a charge, let's say E, right? It tells the world that it exists by exchanging photons, but these photons, right, they can produce a pair of E minus E plus, which annihilates again. So you have this continuous production of these virtual particles. Right? So what happens is that one of these particles is being attracted to the charge, the original charge, right, Q, according to Coulomb's law, and the other is slightly repelled. Now they don't live long enough to actually interact with that, but you know, they do feel the force still. So the overall effect is that we treat the vacuum as if it is becoming polarized and shielding the charge in a very similar way as in a very analog way to what we have in a dielectric medium, right? Now the relevant length scale for all that is the Compton wavelength, right, of the electron. So the relevant length scale is the Compton wavelengths. Which is lambda Compton is just h bar over m e c, 2.4 times 10 to the minus 12 meters. But of course, in natural units, this is simply the opposite of the mass of the electron, because h bar and c is are one, right? And so the dependence of the charge on the distance becomes apparent if we go to smaller distances. But smaller distances mean larger momenta, right? So when the momentum, when P becomes of the order of 1 over lambda C, which is similar to the electron's mass in natural units, then this becomes apparent, right? So we don't see that as long as the particles are not relativistic. But once the energies become comparable to the masses of the particles, then we start seeing this effect, right? So for example, right, at low energies, right, when the particles are all non-relativistic, we have that alpha is 1 over 137, we said that, right? But at something like 90 GeV, the alpha, I'm talking about the alpha, the electromagnetic coupling constant, right? Then it becomes what are you doing? Alpha becomes of the order of 1 over 127. Well, that's QED. Now in QCD, it's somewhat more complicated than that. QED is the simplest. QCD is somewhat more complicated because in QCD, the virtual gluons, they also carry color. And they tend to decrease the interaction at small distances. In QCD, gluons carry color. So they tend to decrease the interaction at smaller distances, small distances. So you might notice that for the electromagnetic coupling constant is increasing with energy. for QCD, it's decreasing. There is a hypothetical scale, the gut scale, where they become identical, maybe, right? So formally, the way to describe that is to use the running of the coupling constant by use of a function which is called the beta function. So you might see that or read about that. So formally, this is done by introducing the beta function, right? Beta of alpha is the alpha over d log of mu, or just mu d alpha d mu, where mu is the energy scale in which we measure the coupling constant. Right. If the beta vanishes, so there is no dependent on alpha on the energy, then we call it a scale invariant theory, right? If beta is equal to 0, then we call it a scale invariant. So given a specific model that describes the interaction, we can calculate beta for that model, right? Remember, the model is derived from the Lagrangian, from the symmetries of the Lagrangian. So we can do the calculations numerically or iteratively. So as an example, just give you the outcome, examples, right, in QED, to the first order. So only one loop, correction. We get that beta of alpha is 2 over 3 pi alpha squared. So when we change the energy, the alpha changes with the energy scale Q. So alpha, the coupling constant alpha of Q squared, scales as alpha of mu squared, right? This is a new energy. Alpha of mu scale divided by 1 minus beta 0 alpha mu squared times log ln of Q squared over mu squared, where beta 0 is 2 over 3 pi. That's for the QED. I'm not going to prove it right now. I don't think I'll prove it at all in this course because we have to do renormalization in order to actually prove it. And that goes, I think, at the end of a second course in quantum field theory.
Is the second line beginning in alpha Q squared a result of the first line?
Sorry, the second line?
Is the alpha of Q squared a direct result from the equation for beta?
No, you go see it directly from beta. You have to do the full calculation. The logarithmic term, you have to do the full calculation.
Okay, thank you.
Oh, I'm not deriving it. It's I didn't derive what is beta here, and I didn't derive this square. I just tell you the result that you know. This is okay. Since beta is positive, it means that the QED coupling constant increases. Right, beta 0 here is positive, so as the energy increases, then the alpha increases. The coupling constant increases. In QCD, again, this is also only for first order perturbation theory. In QCD, again, for first order, only one loop. that's a bit even more complicated. Then you get that beta of alpha strong is minus 11 NE minus 2 NF, and alpha S squared divided by 12 pi. I think I may have a typo here in my notes. I have to check it out. NC, sorry, not NE. NC is the number of colors. And NF is the number of flavors of the quarks. And since we have a minus sign, that means that the coupling constant decreases with energy, right? So at higher energies, the interactions become weaker, which enable people to do perturbative calculations, which is quite good, because otherwise the only way to do calculations in QCD would be to study the bound states, which are the protons and neutrons. Just as, again, jargon, right? People speak about long-range physics, which is the non-perturbative physics, and the short-range, or the physics of hadrons, and the short-range physics, which is the perturbative one, which is the physics of the scattering at high energies. Long-range physics. This is the non-perturbative. Physics of hadrons. And short-range physics. And this is perturbative. And this is physics of high energy, scattering at high energies. Okay, last comment I want to say about that. Any questions?
This is only for QCD, right?
Yeah, this is what you see. Okay, and the last thing I want to say about that is the decay via the strong and electromagnetic. Strong and EM decay. Okay, so, you know, as opposed to the fundamental fermions and to the hadrons, which are in the ground state, hadrons in excited states can decay via both the strong and electromagnetic interactions, right? Because both of them conserve the flavor. Right? Hadrons in excited states can decay via both the strong and the electromagnetic interactions. Right. For example, right, the rho meson, so this is a excited state, right, can decay into a pair of pions, right? So rho meson decay to a pion positive and negative charge, right? We can think of it, it can occur both via the strong interaction. So we have the row meson, right? We have a U bar. So the U doesn't have anything to it. And the U bar can, instead via the strong, produce a pair of a down and anti-down. So this is the negatively charged pion, and this is the positively charged pion. But this can also happen electromagnetically. Guys, correct me when I'm making stupid mistakes.
You reverse the arrows because of the sign of the charges?
Yes. So we have two options for the decay of the row meson. Which one?
You plotted the same one twice.
Sorry?
I think you plotted the same one twice.
This is a gluon.
Thank you.
Thank you. This is a photo. Just not that great at drawing. Okay, so if you want to calculate this process, basically these two diagrams contribute to the process. Which one dominates?
The strong force one.
Of course, right? Why?
Because it's stronger.
Exactly, right? Since the coupling constant, alpha strong is about 100 times larger than alpha QED, then of course the upper one, the strong one would be much more dominant. In fact, if a particle can decay via the strong interaction, that's normally what it will do. I mean, that's always the dominant process. Dominance. It also explains why they have such a short lifetime. Okay, last thing which I'm going to revise with you on the tutorial that is coming right now, but let's finish that first, is conservation laws in the standard model. So, as we know in physics, conservation laws are extremely strong tool in physics in general. And of course, they are essential in particle physics. So let's go briefly over several quantities. And we said that the important thing in particle physics is the vertex. This is the building block of everything. So conservation laws appear in each vertex separately. That's important to remember. So conservation laws at each vertex. Conservation laws in each vertex. So few things which are nearly trivial. So we said the first is the form momentum. It has to be conserved. I didn't really mention it because we didn't really use it, but also the angular momentum. all charges, electromagnetic charge, but all other charges. What else? Flavor. There is one exception. Flavor is conserved for most processes, but which one is not conserved?
Weak interactions.
No, only one part of the weak interactions, the charge currents. Neutral weak, it is conserved, or neutrally charged, except in the charge currents interaction. Another conserved quantity is the leptonic number. And we have a leptonic generation number. So we said we have 3 generations, and we can either call it electron number, muon number, or tau number. So we simply call it leptonic generation number. It can be E electron number, muon number, or tau. And these are also conserved. Also in the charge current interactions. Generally, leptons have leptonic number of +1 and anti-leptons have leptonic number of -1. And anti-leptons -1. You also have baryonic numbers. So because baryons are made of quarks, then we assign a baryonic number of 1/3 to each quark. Baryonic number of, I get a number of 1/3, an anti-quark, of course, -1/3. So that way each baryon has a baryonic number of +1 and each anti-baryon has a baryonic number of -1. And these numbers are conserved. Okay. That concludes what I wanted to tell you about the introductory part of the standard model. Any questions?
The leptonic number is just the sum of the 3 leptonic generation numbers?
No, it's different. It's leptonic number and there is a leptonic generation number. It's 2 separate things. I'll show it to you right away in the tutorial.
So when you say leptons have leptonic number +1 and anti-leptons -1, that's about the leptonic or the leptonic generation?
Well, there are 2 separate numbers. For example, I said that the muon can decay into a neutrino muon, right? And an electron and an electron neutrino, right? Muon decays into a neutrino muon plus electron plus anti-electron neutrino, right? So what is the leptonic number? So on the left-hand side, we have a 1 lepton. So it's a 1. In the right-hand side, we have 2 leptons and 1 anti-lepton. So we have also 1. Now we also have a muon number, right? So we have 1 muon. So the muon and the neutrino muon carry 1 muon number. Okay, so that's called electronic generation in general, but you can call it a muon number. So it's 1 for the muon and for the neutrino muon, right? But it's 0 for the electron and it's 0 for the tau. So we have 1 muon number in the left-hand side and 1 muon number in the right-hand side. And the electron carry 1 electron number. And also the neutrino electron carry 1 electron number. But the anti-neutrino electron carry -1 electron number. So we have 0 electron number on the right and 0 electron number on the left. So all 3 are conserved. Right? That's why in the decay of the muon, we get an anti-neutrino electron and not a neutrino electron.
But here it seems to me like the leptonic number is the sum of the electronic and the muonic leptonic numbers.
Well, it's treated in a different, it's treated as separate quantity. If I think of something that, to prove that, I need to think.
All right.
I'll tell you. I don't have something on the tip of my head at the moment.
Thank you. I need to think. It's considered to be a electronic family number. Right? It's considered to be different than the electronic number. Can you think of a situation? Well, you know, both have to be conserved in order for a process to occur, right? If one of them is not conserved, the process would not occur. Can I think of a process which conserves the total electronic number, but not the, well, yeah, I can actually think of things, you know, for example, a decay of the form muon goes into electron plus, let's say, a proton and antiproton. If you give enough energy, well, that will never happen, right? You know, this is something which conserve, or, you know, plus, right, neutrino E plus neutrino E, an anti-neutrino E. This cannot happen, right? You are conserving the total leptonic number, but you're not conserving the muon number. Yes, I understand this direction. What I ask is how can we conserve the leptonic generation numbers and not conserve the leptonic number? How can you have a balanced number of leptons of each generation, but not a balanced number of leptons overall?
That I have to think. If you have, I'm not sure. I don't know if you can have anything like that. We'll see. Maybe it's the one way. I need to think. I don't have anything in the tip of my head at the moment. So. Yeah. Okay. More questions about that? Okay. Well, I thought it would be faster, but no, I don't mind that much. So now I have a tutorial, which again is based on a tutorial which was given in Tel Aviv on that material exactly. It actually covers pretty much what we just spoke about. And since there's no tutor, it's just that I'm the tutor, then let's just do it, but you try to stop me if there is something which is not clear. All right, so we have 2 parts in the tutorial. One sort of a review on what we just spoke on the standard model. And the second is we do some examples in class.
so that you see, practice a little bit what is possible and what is impossible. All right. Do you want a 3 minutes break, or shall we just continue on directly?
I think we can continue.
One says continue and nobody says the opposite. So we got the one versus.
We can go. We can do.
Sorry?
We can continue.
Continue, okay. So tutorial about the standard model. Okay, so as we said in the standard model, we have the particles and we have the interactions. So the particles, particle content. We said the following. We said we have fermions. These are the matter particles. They all have spin 1/2. We have 6 quarks, right? Which are made of two categories, right? The up, charm, and top. They have electric charge of +2/3. And we have the down, strange, and bottom, which have electric charge of -1/3. And we have 6 leptons. So the electron, the muon, and the tau, right? All have electric charge of -1. And you have the 3 neutrinos, neutrino electron, neutrino, neutrino muon, and the neutrino tau, tau neutrino. They all have electric charge of 0. In addition to all of these 12 particles, there are antiparticles. As anti-fermion counterpart. So anti-fermion is a particle which has exactly the same mass, but the opposite charges. All the charges that fermion carries, it carries the opposite ones. It has the same mass, but opposite charge. So we said first are the fermions. Then we have the force carriers, which are the gauge bosons. These are the force carriers. All of them have spin 1. Since we have 3 forces, excluding gravity here, right? This is a strong force. Then the gauge boson that mediates the force is the gluon. Strong force, or strong interaction. The mass is 0. We have the photon. It's the mediator of the electromagnetic interaction. And of course, it's massless as well. And we have the W and Z bosons. Here, the mediator of the weak interactions. They are massive. The mass of the Z boson is about 91 GeV. And the mass of the W particle is about slightly lighter, about 80 GeV. And then the final particle that there is
is a spin zero particle, scalar, called the Higgs boson. So it's a scalar boson. It's called the Higgs. It has spin zero. Now, if you go to Wikipedia, which I did, you find a very nice table, very colorful table. Just show you how it looks like. You can see my, you see?
I've got it here on my wall.
You also got it on your wall. Okay, so it's the same one. I just copied it from Wikipedia. You just go to Wikipedia, type standard model, and you find all the basic particles in there. Now you can add to that the graviton, but again, this is not something which is normally added. Now these are grouped into 3 generations. It's often convenient to group all these particles into the 3 generations. Again, the reason behind it is related to structural symmetry under the group of the standard model, and how these types of particles, which in the framework of quantum field theory are really fields, transform under the symmetry group. But these are details that I don't think we'll have time to go in this course. Maybe if we go towards the end. So far we're progressing slower than I was initially planning, so I don't know. But maybe because it's a long semester, we have 14 weeks, so maybe towards the end we could speak about these things. So it is convenient to group the fermions into 3 generations. So for the leptons, each generation is comprised of a doublet, a pair, which is really called a duplet, of 1 charge and 1 neutral lepton. So for the leptons, we have 3 doublets. So it's E and neutrino, and muon and neutrino nu, and the tau and the neutrino tau. And for the quarks, we have the doublet, which consists of 1 up-type quark and 1 down-type quark. Right. So again, here we have a charge -1, and here we have a charge of 0. Right. For the quarks, the doublets would be up, down, charm, strange, and top, bottom. Right. Where the charge of the up-type quark is 2/3, and that of the down-type quark is -1/3. Now, generally speaking, the particles in the first generation are the lightest, so they have the lowest mass. And as we go from the first to second to third generation, the particles become more massive. Right, so this is generation 1, 2, and 3. Then generally, when we go from generation 1 to 2 to 3, the particle becomes more massive. Of course, the exception are the neutrinos, which in the classical standard model, they are massless. Today, we know they are not massless, but they have a very small mass. But the origin of this mass is not still fully understood, but everything else pretty much follows this trend, which also means that the particles in the second and third generations are not stable because they can decay. Now, experimentally, it appears that quarks never show up single particles. They exist only in states. So let me write it down. Quarks are never appear. What am I doing? What? Quarks never appear. On their own. In nature. So they only exist in bound states. Right? Of either baryons, which are made of 3 quarks, or of course 3 antiquarks for antibaryons. Right, so such as the proton is made of the up, and down quark. So the charge of a proton, right, is 2/3 of an up plus 2/3 minus 1/3, so it's just plus 1. Or a neutron, which is made up of up, down, and down. Of course, the charge is 2/3 minus 1/3 minus 1/3, so it's just here. This is the first type. And the second type is meson, which is a pair of a quark and antiquark. Right? So for example, the pion, right, is made of up and anti-down. So the charge of the pion, right, is 2/3, right? Plus down is minus 1/3, but anti-down is plus 1/3. So we can say of a minus 1/3. So it's a plus 1 overall. And as I stated, this can be understood with the use of a color charge. Or maybe I should say that these can be used, can be understood. Using color charge, right? We say that each quark is carrying a color. Color, which can be either red, can be green, or can be blue. Right? Of course, anti-quarks carry anti-color. Right? So the only states that are allowed in nature are white, so total 0 color.
Careful when you say that these days.
Why?
Eyad, explain.
Thinking about states.
In some state, it is problematic today.
White color equal to 0. Well, this was constructed in the 60s. Which means that there are a combination of 3 colors. So a combination of 3 colors, right? So we have a red plus a green plus a blue, right? Or a color and an anti-color, right? Or color plus anti-color, such as red plus an anti-red. It gives us white. Now, color-free states of quarks known as hadrons. Hadrons. So basically, hadrons is a general name which contains both baryons and mesons. Now, of course, these are just heuristic descriptions. We don't see, we cannot measure any color charge. And obviously, these are nothing to do with the colors that we're used to from our everyday life, right? But this is a formalism that helps understanding the mechanism behind this hadron formation. All right, questions? No questions? Okay. So conservation laws. I said that we don't already go, let's say it again because of the importance. I think also I might include a few more here. So the relevant quantum number is conserved. The following quantum numbers are conserved. So we said the 4 momentum. We say the angular momentum. J is L plus S, right? Orbital and spin. The electromagnetic charge. We have the flavor. They are conserved in the strong and electromagnetic. Conserved in strong electromagnetic. So the only way to get rid of an electron, right, is to annihilate it with an anti-electron. If you want to use the strong and electromagnetic. And then we said there is a leptonic number. L, which is defined as +1 for any lepton. -1 for any anti-lepton. And 0 for any non-lepton.
And then the lepton family number. Generation number. So it's the same, only for each lepton generation separately. I honestly cannot see a way in which the lepton generation number will be conserved and the total net lepton will not. I think it's just for ease of quick calculation. It's easy to think of that, or maybe from historical reasons. Honestly, I don't know. E neutrino E, muon neutrino muon, tau neutrino tau, tau neutrino. You also have the baryon number. Again, it's called B. So we have B is 1/3 for any quark. It's a minus 1/3 for any anti-quark. And it's 0 for any non-quark. Which means that it is 1 for any baryon, minus 1 for any anti-baryon, and 0 for the meson.
Isn't quark plus 2/3 charge?
Sorry? No, baryonic number, it's not the charge. Electromagnetic charge is something different than the baryonic number.
Sorry.
No, sorry, it's okay. And then we have the quark family number. Right, again, each quark generation separately. Right, up and down, the family, and charm and strange, top and bottom. Each one is being conserved separately. So the form momentum, angular momentum, and the electromagnetic charge are conserved in all standard model interactions. Now, the strong electromagnetic and the neutral weak. So those interactions mediated by the Z boson, they conserve flavor. And if they conserve flavor, that means that all other quantum numbers are also conserved. Numbers. Now the charge weak, right, the one mediated by the W interactions. Of course, they cannot conserve the flavor. Flavor necessarily changes. But the leptonic number, the leptonic family number, and the baryon numbers are conserved. Leptonic number. electronic family number, and the baryon number, they're all conserved. Now the quark family number is not conserved. Maybe this actually answers your question. Right? Because a W can connect quarks from different generations. It's true for the quarks, not for the leptons. So to make a small table summarizing everything. The table will go something like that. We have the strong, we have the electromagnetic, we have the neutral weak, and we have the charge weak. Then let's see, for momentum, angular momentum, electromagnetic charge, flavor, then lepton number, and then lepton family number, and then baryon number, and then quark family. So the form momentum is conserved by all of those interactions. The angular momentum is conserved by all of those interactions. The electromagnetic charge is conserved by all of those interactions. The flavor is conserved by the strong, the electromagnetic, and the neutral weak, but is not conserved by the charged weak. The lepton number is, for the strong, this is irrelevant. So the lepton family number is irrelevant, but is conserved by the other three. The lepton family is also conserved by the other three. The baryonic number is conserved by all of those. And the quark family number is conserved by the strong electromagnetic and neutral weak, but is not conserved by the charged weak. All right. Questions? Okay. No questions? Then let's do some examples, some exercises. So I'll give you several possible interactions, processes, and you tell me whether this process is allowed by the standard model or not. Okay. So, question. For each of the following processes, determine whether the process is allowed, and if not, then what conservation laws does it violate? Determine whether it is allowed, and if not, what conservation law does it violate? Okay, so let's start. What about two proton scattering that result in pions? It's an easy one. Is it allowed?
No charge.
Right. That's one thing. More?
Baryonic number.
Baryonic number, very good. So this is forbidden, of course. And there are two reasons, right? One is violation of electromagnetic charge and of baryonic number. Right? So what is the initial baryonic number? 2. What is the final baryonic number?
0.
Right, so it's violated. What is the initial electromagnetic charge?
2.
2. What is the final electromagnetic charge?
0.
0. So right, so B initial is 2, B final is 0, and Q electromagnetic initial is 2, Q electromagnetic final is 0. Not allowed. Okay. What about, what do I have here? Okay, it's going to be easy. Proton, and the proton goes into two positively charged pions. Allowed or not allowed?
No.
No, why not?
Baryonic number?
Baryonic number, very good. So this is also forbidden. Right? I mean, the pions are also made out of quarks, right? But the baryonic number of the protons, right, B proton is 2, and plus 2, right, which is different than B of the pions, pion plus, pion minus, which is 0. Right? As far as the electromagnetic charge, there is no problem. What about proton and an antiproton? Goes into a pion plus and a pion minus. Is this allowed?
Yes.
Yeah.
This is allowed. It's more difficult for me to follow, especially that some of you don't open your cameras, but I do want to encourage also those students that are less participating. This is exactly for you. To participate and show that you're with everybody. It's easy to get lost because there are a few that are a little bit going understand slightly faster than others, but I want everybody to participate. So this is of course allowed. Allowed.
So for this to happen, we needed to have some quarks and anti-quarks annihilate each other.
Yeah, that can happen. There's no problem. What about the following? What about the proton decay into a neutron plus a positron plus an electron neutrino? Is this allowed or not allowed? What do you say?
Are the regular neutrinos the ones with -1, or the antineutrinos the one with -1 leptonic number?
Antineutrinos have the minus. Neutrinos have the last one. Leptonic number. You can look at the table. Well, it's up there. But,
So looks fine.
looks fine. Are we liking to see this picture? Well, guys, we had one answer. I want more people to answer. Is this allowed or forbidden?
Allowed.
Allowed. Okay, we have two allowed. It's two answers. Right. This is forbidden. Why? We don't see protons decaying in nature into neutrons. Why?
Center of mass energy?
Yeah, it violates the energy momentum conservation. Now you may recall that the neutron is slightly heavier than the proton. The mass of the neutron is 938 MeV, and the mass of the proton is 934 MeV. So that means that when we go to the, this is a decay process, so we can always go to the rest mass, the rest frame, the frame in which the proton is at rest, right? And of course, the total energy in the final state cannot be greater than the total energy in the initial state, right? You cannot have that E final is greater than EI, which is just the M proton.
Two questions.
Right?
One, the 934, should that be a 931?
To the best of my knowledge, it's a 934. But this is something which you can just go Wikipedia.
Okay. And if we added a photon on either side, then it could be done?
Yeah, it can happen inside nucleus. That can be. Because then you can if you can grab some energy, but this would not be just a decay the way it's been described here. So it cannot happen. If you have a free proton, it will never decay into a neutron. But if you have a proton which is bound in nucleus, this can happen because there is another source of energy. What you're describing is that if you have this proton interacting with another particle, but then it's a scattering process. It's not a single particle decay. Is that clear to everybody?
Yes.
Okay, let's proceed. What about the muon K to an electron and anti-neutrino electron? Allowed or forbidden?
Forbidden.
Why?
Generation number?
Very good. Lepton number and lepton family number. Violates two things. This is forbidden. Right? Violates both lepton number and lepton family number. right? What is the initial lepton number?
1.
1, right? L initial, it's just the L of the muon. It's just 1. And what is the final lepton number?
2.
0, very good, right? L final, just L of the electron plus the anti-neutrino. So it's just 1 minus 1, it's just 0. There is a violation. Also, what is the muon number initially? The family number of the muon, right? So L muon initially. What is that?
1.
1, right? We have 1 muon. What is the electron number, electron family number initially?
0.
0, right? What is the muon number in the final state?
0.
0, there are no muons. What is the electron number in the final state?
0.
0, right? We have 1 electron, but 1 anti-neutrino. So it's a 1, again, it's a 1 minus 1, so it's a 0. So the electron family number is actually conserved, but the muon family number is not conserved. What about the muon decaying into an electron plus anti-neutrino electron plus neutrino muon? What about this one?
Allowed.
Allowed.
That's all.
What? This is allowed.
Yes.
That's the only allowed way. Allowed. This is the only allowed way for a muon to decay. This is the only way for a muon to decay. What about, let's speak about scattering now. What about electron and a positron? Well, annihilating into up and anti-charm quark. Allowed or forbidden?
When you put the plus, you mean the quarks are in a down state or not?
I mean a what? No, I mean an up quark plus an anti-charm quark.
No, they can't be alone.
Up quark plus an anti-charm quark. You start with an electron and a positron. They annihilate and they end up with an up quark and an anti-charm quark. Can this occur in nature?
No.
Why not?
Color for starters.
True. What do you mean color? Define color.
You can't have quarks on their own. They have a color. They won't.
Together, they'll form a meson. You have a meson is form of a pair of a quark and anti-quark.
So they are bound together.
Yeah, bound, yeah.
Ah, okay. Thought they were alone. But electrons don't have color.
Yeah, so what? Initial color is 0, final color is 0.
I think it can happen, but only using the charged-weak interaction.
Okay, more suggestions? Come on, guys.
This is not satisfy the color confinement.
No, you up and charm, anti-charm can be confined. I don't remember by heart the name of the particle. You can check it out on PDG. Just go to the PDG and see. So the answer is no, of course. This is forbidden. Why it is forbidden? What are we violating here?
Oh, no.
What?
The electric charge?
No. Electric charge is 0 at the beginning and is 0 at the end.
The quark family.
Thank
Quark
you.
family.
Thank you. Very good. It's a quark family number violated. And also the flavor.
Didn't we say that the charged-weak interaction can change both of these?
It can change. Wait, hold on. We said that the charge-weak interaction, yeah, it can change both of these, but then you will have a different charge, right? Because the charge weak means that you're changing the charge, right? You
No,
don't have
sorry,
a
I don't get it.
Okay, you don't have a way. You start from an electromagnetically neutral initial state, right? The total charge initially is 0. And you end up with another electromagnetically neutral state, like the up and anti-charm quark, right? And you cannot do that mediated by an electrically charged
W boson?
W plus minus boson.
No,
Okay.
sorry, I don't see it.
You start from an electric charged particle, right? And you start from an electrically neutral combination, right? So you cannot go from an electrically neutral combination via a charged interaction, charge-weak interaction, to another electrically neutral interaction.
That's what I don't get. Why?
Your boson for the charged weak interaction itself carries charge.
Okay.
So it can't leave two neutral or two combined neutral particles because it itself has a charge.
Sure, but why can't the electron?
Going again. If you have the boson, what Ofek says is correct, of course. You have a boson, the boson carries a charge.
Yes.
Right, so it needs to interact. When it interacts, it brings this charge somewhere to someone.
Yes.
And you don't have it here. You have a situation of an electrically neutral outcome.
No, so maybe I'll ask you that after the lecture because I don't get it, sorry.
So we have here the lepton number and the family number.
and the baryon number are all conserved. But since we have a change in flavor, right, then the only way that it can occur is via interaction of exchange of a W plus minus. Via exchange of the W. But we cannot go from electromagnetically neutral initial state, E plus and E minus are electromagnetically neutral, to another EM neutral state, with an electrically charged W. So this is forbidden. Okay, we are really running out of time, so let's do quickly the other ones.
Wait, if instead of an anti-charm, we put in an anti-top, so that would have required two charged weak interactions?
Would it mean
No, this would be not balanced.
It will be exactly the same.
It's the same twice.
Well, if you have, well, let's look at that. If you have a E plus, E minus goes into, let's say, a charm plus an anti-charm. What about that? Is that allowed?
Yeah, that's fine.
Yeah, this is allowed. That's right.
You can always exchange any particle and its antiparticle with any other particle and its antiparticle because all the charges are zero.
Well, I'm not sure what you mean by exchange, because I don't have a decay, for example, of the electron or for the muon into a charge and anti-charge.
No, but if you have if you have a particle and its antiparticle,
Yeah, okay. Yeah.
if you have enough energy in the center of mass frame, you can get any other particle-antiparticle pair if they're the same. Because all the charges are plus minus the same. So all charges are zero.
Yeah, that's true. So here you have everything is zero, that's fine. What about, let's go fast because we're running out of time. What about E electron and a positron ending up with a photon? Is this allowed?
No.
Okay, someone else has more ideas? More suggestions? Yes, no? What do you say, guys? Allowed or not allowed?
I think it's forbidden.
Okay, we have two that says it's forbidden. Why do you think it's not allowed or forbidden?
Because it's somehow the inverse of what we had before with the proton that couldn't, like, you can't create a single photon. You need two photons, I think. Because in the center of mass system, the photon will have to be stable, which static, which can't happen.
Again, because it violates energy momentum conservation.
right? Because at the center of mass, again, you can always go to the center of mass frame, and then the total initial momentum is 0, the 3 momentum, but we do not have any photon with a 0 momentum in any frame, right? In the center of mass frame, P total initial equal to 0. And there are no photons with 0 momentum. And then the last one, I know I'm running over time, but I'm compensating for the lost time. What about E plus and A minus goes to 2 photons?
Yes, because they can compensate for the overall momentum.
Exactly, very good. This is allowed. Okay, guys, I apologize for taking too much of your time. Of course, if you go in the center of mass frame, then after the interaction, the outgoing photons will have the same energy and they will go in the opposite directions in the center of mass frame, of course. Right? I'm sorry for taking too much of your time. You'll get more of these in the homework set, in the problem set, which I will post on the web today. You'll get about a week, slightly more. And I know that several of you have submitted the homework. That's great. I'll grade them. And that's what I have to say. So thank you very much.
Thank you.
Any further? Okay, let me.
תודה רבה.
לכם. We can do the stop share and I can do the stop recording.